Hello everyone, myself Prashant. In this video, I'm going to say you what is hole or how to fix hole. Let's move on. First of all, what is hole? Minimum time required for the data to be stable after the active clock edge is called hole requirement. That means as soon as we receive the rising edge, uh, the data will start capturing by the register. So it takes some time for the data capture process. So when the data is being captured by the register, the data shouldn't be changed. That means it should be stable for some time. So that minimum time for which the data should be stable is called the hold requirement. Or in other words, we can say the data which is being captured shouldn't be disturbed by the data launched on the current edge. So let me show you what I'm trying to say. So these are the two waveforms which we have. So the first one is the launch clock and the second one is the capture clock. So the data which is launched over here will be captured over here. In the same way, the data which is launched on the second cycle is going to be captured on the third cycle. So the data which is launched here, the green one, so will be captured. The register starts capturing on this edge, but it takes some time for getting it captured completely. That means that is what we call as hold requirement. So after this active clock edge also, the data should be stable for some amount of time, and that is what we call it as the hold requirement. So due to some reasons, so the data which is launched over here, so if the data part delay is so less, so we have slight chances of getting this data captured within this window. So and the data on the D pin might change. So that is going to lead to a hold violation. And this is what is one of the important check which we'll be doing, and we have to fix it, and we don't have any kind of waivers on this hold in general. Okay, let's move on. Okay, in the following slides I will be explaining you, or I will be showing you what is in the cases where we can see the hold violations and how to resolve them. Okay. The case 1, here you can see we are having the two registers, register 1 and register 3. We don't have any data path. That means that we don't have any cells in the data path. So we have, in these cases, we'll be having more chances of seeing the hold violation. Next case, the case 2. Here you can see we are having the two registers again, register 1, register 3. But the data is muxed and is going to the register 3. So we can say we are having two paths over here. One is from Q through this combinational path and the mux and D. And the other one is from this Q and straight away going to the mux, and then it is going to D pin. So we can say the first path is the largest path and the second path is the shortest path. If at all we are saying that we are having the whole violation from register 1 to register 3, we can say the whole path is from this. So from Q to the mux and then to the D pin. So this is the shortest path, and this shortest path will or can damage or can disturb the storing process. So whenever the previous data is being captured over here in the register 3, the other data can come through the shorter path and disturb the data which is going or which is being stored in the register 3. Case 3, we have two paths here, the same, the register 1 to register 3 and register 2 to register 3. So register 1 to register 3 is the longer path and register 2 to register 3 is the shortest path. Whenever we are storing or we're in the process of storing the data which is launched by the register 1 in the previous edge, and it is being stored in the register 3 on the current edge. So in that process, the whatever may be the data which is launched by the register 2 can come and disturb the storing process, and the data will not be or may not be stored properly in the register 3, and that in that way, or we can say that we are having the hold violations. The case 4. So whenever we are having the positive skew, so you can say from this diagram, the clock signal is going to the register 1 faster than compared to clock signal which is going to the register 3. So I can say the you can see here this is the launch clock cycle and this is the capture clock cycle. The previous data which is being stored here will be captured over in the on this edge, and even we are having more chances of now we have more chances of this data which is launched over here on the second edge being captured on the second edge itself. So whenever we are having the positive skew, that means it is very bad for my hold and we have more chances of seeing the hold violations. Case 5. Here you can see the start point is the register 1 and the end point is the macro. So generally macros may have more hold requirements or more library hold requirements. So when we have more library hold requirement, that means data should be stable on its deep in for more amount of time than compared to my regular register. So regular register might need on the for the regular register data might be need to stable for maybe some 10 picoseconds or 20 picoseconds. For the macro, which is having more library hold requirement, after the active clock edge, the data on its deep in on its input should be stable for maybe more than 500 ps or 200 ps or something like that. So that means macros generally will have more library hold requirement, and that means we need to have we need to keep the data stable for more amount of time. So these are the cases like where we can see the hold violations. Now let's see how to fix the hold with some examples. So in this first example, in this first diagram, you can see we're having reg 1 to reg 3 timing path and we don't have anything in the data path. So when we don't have anything in the data path, we are going to see the hold violations here. So in order to fix the hole, I have added two buffers in the data path. So when we are adding two buffers in the data path, reg 1 to reg 3, it takes some delay from reaching the Q pin of reg 1 to D pin of the reg 3. Earlier, there was no delay in reaching from Q to D pin, from reg 1 Q pin to reg 3 D pin. Now when we have added the buffers in the data path, it takes some time to reach from reg 1 to reg 3, and that is going to serve the purpose, and the hole will be fixed here. Okay, the second way to fix is the divergent point fixing. In the first diagram, you can see we are having two paths. One is from register 1 to register 3 and other is from register 2 to register 3. From the data from the path from register 2 to register 3 is the shortest path, whereas from reg 1 to reg 3 is the longest path. That means we are having more data path delay in the register 1 to register 3 path. Obviously, I can say when if at all my hold is violated for register 3 as an end point, the hold path can be obviously from register 2 to register 3. In order to meet the hold, we can add a buffer on the D pin straight away. If at all we are adding the buffer straight away on the D pin, we have huge or more chances of getting the setup violated in the reg 1 to reg 3 path, because we already have some amount of data path delay in this path from reg 1 to reg 3. If at all we are adding any buffers in this path, that is going to obviously violate or may violate reg 1 to reg 3 setup. So in order to avoid that, what we can see or do is we can try to find out the point where hold is violated but we have more setup margin. One such path is on the input pin of the mux. If at all we see the delay or the setup margin from reg 2 to reg 3 through the mux second input pin, we can say will see more setup margin, and if at all we are adding hold buffers in this path, we can say my hold is met, or we can meet my hold violation. At the same time the setup will not be violated. So this point where we are having more setup margin and hold is violated is called divergent point. So in this example, we have four paths: reg 1 to reg 4, reg 2 to reg 4, reg 3 to reg 4. Sorry, three paths. We have three paths. I can say if at all my reg 4 is hold violated. So we can see, we shall see where all we can add the hold buffers to fix it. If at all we are adding the hold buffer over here, so it is going to violate reg 1 to reg 4 timing path or reg 3 to reg 4 timing path, because we are having obviously more amount of data path delay in these paths from reg 1 to reg 4 and reg 3 to reg 4. So this may violate my setup of these two timing paths. If at all we are adding the hold buffer over here, so that's again going to violate my reg 3 to reg 4 timing path. So we cannot add buffer over here as well. If at all we are adding the buffer over here, so that means it is going to violate my reg 1 to reg 4 setup. So it may be not disturbing any setup of my reg 3 to reg 4, but it may degrade our setup of reg 1 to reg 4 path. So again, we cannot add buffer in this path. And here we can say that reg 1 to reg 4 again will violate my setup. So the only option which we have over here is to add over here on the second pin of this AND gate. So then what happens, it is not going to disturb my setup timing of reg 1 to reg 4, and not only that, it will not disturb my reg 3 to reg 4 setup path. At the same time, if we are adding the buffers in on the second pin of this AND gate, it is going to fix my hole and it is not going to disturb any of my setup timing. So this is other example of my divergent point fixing. So if at all in the practically, whenever you're trying to fix the hole, you can kind of see the setup margin on all the input pins rather than checking on the output pins. So you need to check the setup margin on the input pins, and wherever you're having the input, wherever you're having the setup margin, you can straight away add buffers in that path that is going to meet your hold violation and not going to hamper or disturb your setup violations. If you have few picoseconds of the hold left to fix, you can try some of the following techniques to address that hold. So let's assume this is the scenario which we have, register 1 to register 3, and we are having the zero skew in between this in between these two registers, and for some reason the hold is violated in between register 1 and register 3, and let's assume that is violated by some few picoseconds. The first thing we can try and do is upsize a buffer in the capture clock path. If at all in such a way that the capture path delay is reduced. If at all we are able to upsize one of the cell in the capture clock path and manage to reduce my capture path delay by few picoseconds, that is going to reduce the skew by few picoseconds, and which is going to reduce or your fix your hold violation which is violated by few picoseconds. The second one is we can downsize a buffer in the launch clock path. So in such a way that we have to increase the launch path delay. So whenever we are downsizing a buffer in the launch clock path, and if at all we are able to increase the launch path delay, that is going to reduce your skew, and which in turn is going to fix the few picoseconds of the hold left, or which is left unaddressed. We can convert some of the cells in the data path to HVT. So if at all we are having some of the cells in the data path and we are going to convert them to HVT, that is going to increase the cell delay, and which is going to reduce or address the few picoseconds of hold violated. We can even add a dummy cell in the launch clock path in this fashion. That means output is floating and we are just connecting or just increasing the fan out of one of the driver in the launch clock path. So then the launch clock path delay is going to increase, and when it is going to increase, your skew is reduced and again your hold is addressed. So yeah, these are some of the techniques which you can use to fix the. Yeah, so this is about today's video presentation. So happy fixing hole. Thank you.